Okay, when we're studying rigid body motion, um, we have to sort of modify our idea of mass, because what we have a situation here where we have a distributed mass. The mass isn't concentrated at a single point where we're just going to be able to take the mass of that point and apply be able to calculate momentum based on its movement and everything like that. Now we have a distributed situation where not only is the mass distributed, but the effects of applying a torque and the effects of rotation also uh, provide like a distribution of velocities within the object. All right, and so what I have here is a representation of some random object, right? And I've chosen, although this isn't strictly speaking necessary, at least for the first part of what we're going to be discussing, I've chosen to locate the coordinate system at the center of mass, G, of this object. Okay, now this object is undergoing a rotation signified by the angular velocity, omega, and then we picked out a random point within the object, and its position is signified by the position vector r. Now, what's going to happen as omega signifies the rotational speed of or the rotational velocity of the object, and as a consequence, the velocity of the point in question travels in a circle around omega, is traveling at least instantaneously along this path, this circular path around omega, centered with the axis along omega. Okay, now if you remember, the angular momentum was given by that position vector crossed with the linear momentum. Okay, the angular momentum of this point around, the angular momentum of this point about the origin, in this case centered at the center of mass of the object. Now, so the angular momentum is given by the position vector crossed with the linear momentum of the point in question. And the linear momentum is mass times velocity, so the angular momentum is just mass times this cross product, r cross v. And in the case of rigid body rotation, we have, if you recall, the velocity is going to be omega cross r, right? So omega cross r, that would be, in this case, as drawn here, omega cross r, so it'll be a vector that's perpendicular to both omega and r and follows the right-hand rule, which means it'll be rotating, as depicted here to the left around this fashion right here. And that makes sense, right? So v at this instant is pointing kind of off in this direction like this, and it's following this path at all times, right? And this is kind of a review. So the angular momentum can be rewritten oops. If I just take v, substitute in omega cross r. All right. Now there is a, if you recall, one of your homework problems will have been this property of cross products like this. So this is called the vector triple product. And if I have three vectors A, B, and C, this is equal to so this is a general statement for the a triple, the vector triple product is what it's called, between three vectors. And so H then becomes so what's interesting here is that H isn't simply directed along omega. There's also a component like a pointing in the opposite direction as R, right? And given by this relationship. So in this case, we'd have the angular momentum of this particular particle wouldn't necessarily be directed straight along omega. It's also got this thing where it's going to have an aspect of it that's pointing slightly in the direction of negative R. All right. So we can expand this out. We can take these dot products. So R dot R is just the magnitude of R squared, right? And then well, okay, here, let's expand this in terms of its components. And we can do that for X, Y, and Z. Okay. And these coefficients, we group them, we can give them another name. Okay, that's ultimately all we're doing here. And so we can define say for hx, we can say that this is equal to these coefficients. where the coefficients are defined this way. Okay, where m is the mass concentrated at the particle in this case. All right, so the mass in all of these cases, we're talking about this single particle. Okay, and then we'll expand it to include distributions here in a second, but it expands pretty straightforwardly. So likewise, we can define the same thing for the other two components. Where the coefficients are defined in this way. These are called products of inertia, and then these would be called the moments of inertia about the x-axis and the y-axis, and the z-axis when we get to it. Okay. Now notice a couple things before we move on. Notice Ixy is negative mass Rx, or Ryrx. Well, that's the same as Iyx. So just to drive that home, the coefficients Ij are equal to the same coefficients if I reverse the order. So if this is kind of common notation, right? All right. So we can these I coefficients, these coefficients that I've labeled with I, and then the subscripts for the letters or for the axes, is what's called, or the collection is called the inertia tensor. And we're not going to get into tensors in general. It's a fascinating. To be honest with you, it's an interesting topic, and I encourage you to at least research it a little bit. But what it does actually simplify a lot of things that seem really complicated when you don't have that powerful notation. But for our purposes, the inertia tensor, which I'm going to signify of the letter I in this bracket notation, so we can arrange that these into a 3 by 3 matrix. Now, not all tensors can be arranged into matrices, but it just happens to work out in this case that we can. And the interpretation is really useful when we can employ some mathematics behind linear algebra and whatnot to get a better understanding of how to manipulate, in this case, the inertia tensor. And so now, so this is a representation of a tensor. It's not the actual tensor itself. That's not going to be an important distinction for this for this class, but and it has this property that the transpose is equal to itself, right? So what I'm saying here is that IXZ is has the same same value as IZX, and likewise for YX and XY. These, if I flip these around the diagonal, so here's the main diagonal. If I swap these two, and then I swap these two, and then I swap these two, you wind up with the same. And that's easily seen from the discussion we just had. Now, so why would we do this? In this case, we can represent the components of the angular momentum and the angular velocity and when we do that, when we represent these as column vectors, when we represent H and omega as column vectors, we get this situation. And so we can write this simply as So now there's a simple mapping between the mass distribution. But okay, so we haven't yet calculated I for a whole distribution of mass, but that's a simple process that I'm about to get into. But now there's an easy, sort of a powerful notation to relate the angular momentum with the angular velocity through what's called the inertia tensor, and using the mathematics of linear algebra and matrix multiplication. Then these, this is just a simpler way of writing this statement, and I think a much more sort of intuitive and powerful way of doing it. So now the question is, how do we find I? Okay, so for a collection of particles, it's quite simple. Then, so for a collection of, say, n particles, let me write that better. If we have n particles, the total inertial tensor for all of the particles is just the sum over all the particles of the individual tensors. So I sub j would be, say, the inertia tensor associated with this single particle. And if we had a series of a whole bunch of particles, we can just simply add them up. So what does this mean? How do you add a matrix if you guys if you're not completely familiar? Well, it's just component by component, just like just by like a vector. So the so for the component of the total, so the Ixx component of the total inertia tensor would just be the sum of the individual components, and likewise for xy and so on, xy, xz, and so on and so forth. So for a continuous body, we have to take a step back, and these summations have to become an integral. Meaning, so we have to integrate over the distribution of mass. And so to do that, all right, so if the body is continuous, we can't just add up a series of discrete particles. So this summation here becomes an integral. And so in that case, we have to take the integral over the volume of the density as a function of position, right? So you can kind of see the similarity between this and this, whereas now, rather than having the simply the mass of the particle, we have to integrate over the volume of the particle. But it's essentially the same, where rho is the density. the mass density, maybe, just to be super precise. And it's a function of the position within the object, you know. So in general, the density within here could vary with position. It won't be important for us. We'll be dealing with constant densities, I think, without, unless I'm giving it to you explicitly or something like that. But however, in general, the mass could be distributed other than uniformly. And then for these mixed, or the products of inertia, say, and so, you know, I could write this out again. So for Ix, in sort of a more general statement, I'll write these ones out, but and then for the other off, so the non-diagonal terms, so for the other terms that are off of the main diagonal, we can sort of summarize it this way. Again, where J and K go from 1 to 3, however, J does not equal K. Okay, so that's just saying X, Y, XZ, you know, YX, YZ, and so on. All right, so all of that depended on our choice to locate the, you know, the X, Y, and Z coordinates all depend on where we decide to put them, right? In this case, and in most cases, we at least start out with putting these at the center of mass of the object. It works out to be convenient to do so. So now we're going to start with, all right, so we didn't have to necessarily choose this orientation for X, Y, and Z. Okay, we could choose, you know, any orientation we'd like. However, there is a particular orientation and a certain special orientation Now this orientation is described by three vectors, right? In this case, we chose x, y, and z somewhat arbitrarily. But we could choose x, y, and z to coincide with what's called the principal axes and in that orientation, or in those orientations, I can be what's called diagonalized. And it's exactly what it sounds like. So in those cases, maybe we'll call it well, in those cases, the tensor takes on this simple form. Okay, and that's often what's given in these tables. So if you look in the back of the textbook, you're only given three quantities. Maybe you can see it. Anyway, XX, YY, and ZZ for these simple geometries. Okay, now you're only given three quantities. You're not given the 6 independent quantities necessary to fully define the tensor, and you're doing that. They do that because of the fact that it is in what's called the aligned in terms of the principal axes. Okay. There you go. So you can see, like, for each one of these shapes, parameterized as shown, if the coordinate system is oriented as shown, it's usually, you see how sort of intuitive it is. So the principal axes happen to align with axes of symmetries of the object for the most part. Okay. And so they're aligned in like sort of what you would expect. Like for the rod, you have an axis. The z-axis goes along the length of the rod, and for a disc, you have the z-axis sticking straight out of the disc. So in this case, they chose to orient z in terms of this axis of symmetry. So rather than computing the integral every time we need to determine the moment of inertia, we can utilize these tables, but we have to be able to translate. We have to be able to translate what's given in the table to the orientation that the problem dictates, the orientation and sort of position that the problem dictates. So we'll have to we calculate something called the moment of inertia. Now remember, these are individual moments of inertia. This is about the x-axis, this is about the y, and this is about the z. But what if we need it about some arbitrary axis? Say we need the moment of inertia. Say we need the moment of inertia of this cylinder, but on an axis that's sort of oriented in some random way. Well, to do that, we take the inertia tensor and we have to act on it with this axis, this new axis that we're interested in. So if we have this angular velocity equal to a scalar, the magnitude, times n, where n is a unit vector, and it basically just signifies the axis with which we are rotating, right? And omega, the scalar omega, is how fast we're rotating. Then alright, so we get a scalar value. So this is just I. Maybe I could call it I sub n, just for just to be in compliance with the notation here. So the moment of inertia about this arbitrary axis n is equal to that right there. So you can compute. I'll leave it to you to do the actual calculation, but if you perform, so you take the this matrix and you multiply it by n, represented as a column vector, and then you take the dot product of n with that, you arrive at this sort of complicated looking, that's not complicated, but lengthy expression. Now, so you got to be careful that n and I, when I refer to x and nx, they must be described in the same coordinate system. Typically, we use the principal coordinate system, or the principal axes. In which case these will be 0, right? So if the principal axes are used, now that's kind of it sounds easy enough, right? However, these objects will be rotating and translating and doing all kinds of complicated things. So these principal axes are going to be rotating and translating and all this other stuff. So that's when things kind of get, we need to be careful about what we're doing. Now, all right, so some of you might be getting concerned that this is getting really complicated, right? I'm going to kind of leave you in this complicated state here at the end of this discussion, but we're going to come back around, and the problems that we're going to be doing are going to involve a great deal of simplification, at least at first, and then we'll come back into the more complicated situation where we're going to be doing arbitrary 3D motion. All right, so don't get too concerned yet. So if this is the principal, this is if x, y, and z are the principal axes. Hopefully that's spelled right. And centered at the centered at the center of mass, and the origin's position at the center of mass typically. Now, all right, so we've dealt with the idea that we're going to have to be able to rotate those axes and arrive at a moment of inertia around some arbitrary direction. But what if we need to move it from, say, the center of mass to maybe it might be more convenient to describe this moment of inertia about like a fixed point, like this body might be pinned down at a point other than its center of mass. To do that, if you notice, these are given, it says so in the title here, the center of gravity and the mass moment of inertia, they're centered at that point G, the mass, the center of mass. So we may have to be able to, what if we have to translate it? Like you have a situation here where you have axes that are located at the end of the rod versus in the center of mass. That's a common thing. If you have like a mechanism or something where one of the links, you're not going to, typically you're not going to pin it down at the center of mass of the link. So if we need to translate so if I have a point, so if I need to translate it, then the moment of inertia, we're talking about just the scalar moment of inertia. Okay, just the single number. That's going to be equal to the scalar moment of inertia calculated as it calculated from the center of mass plus this additional term. Now this turns out to just be a correction, and it's essentially it represents the what the moment of inertia would be if the total mass were concentrated at G. Okay, so here you have the moment of inertia of the object as it rotates about G, and then we needed to correct that. So if we're going to rotate about, say, some other point, so this thing's going to be doing this, well, the moment of inertia of the total mass concentrated at G now adds a correction factor. So we were calculating, so if this is G, we can look up in a table or something, or even compute it in a CAD program. A lot of CAD, I mean, it's not even a lot. All CAD programs, as far as I'm aware, will give you stuff like this mammoth, a way of calculating the moment of inertia around G. And then say I need to rotate about some other point for some reason. The correction is really just the idea that is essentially equal to the concentration of all this mass into the point G, and then the moment of inertia that you would get for about the point at which you're trying to rotate. You follow what I'm saying? So I have the moment of inertia due to the actual distribution of mass, and then I have to correct it because I moved it as if, and the correction is essentially the same as if I concentrated this mass at G, and now I move that particle with the mass concentrated at G about the origin that I need, the new origin that I need to calculate about. So it represents and RG cross N, it's kind of a complicated, well, it's not complicated really, but all this represents is so if this is R, and this is, say, N, it's the perpendicular distance. So we're taking the magnitude of R cross G, and that's just going to give us this value right here, which maybe we call D. Okay, and then M times D squared, the perpendicular distance from the position of the particle to the axis of rotation. It's the minimum distance from the, and so this is called the parallel axis theorem. Okay,